Okay, I'll make that 2 minutes past. We'll make a start. If that's okay with everybody else, we can admit others as they join. First of all, thank you very much for joining us for this session, where we'll be providing an introduction to asset health and risk. Just a very quick introduction from myself. My name's Chris Given. I'm Strategic Bid Manager here at EA Technology. I work within our consultancy insights business, where we support businesses, local authorities and energy networks with strategic decision making through a range of consultancy and software services. We also have Joanne Peacock with us, who heads up our asset investment management team. Over to you, Joanne.
Yes, that's me. I think Chris has introduced me, so just really helping network operators, industrial customers, anybody who comes into contact with electrical assets, just help them make better asset investment decisions through the use of teaching sessions like this about asset health. We have a webinar series that it's free to attend, and then also through our consultancy and software provisions as well. But we won't bore you with those today. Today is all about asset health and risk.
Thanks, Joanne. Just a quick note, we are recording this session just so everybody is aware, and we can share that later on in due course. Okay, so just a quick look at the agenda for today's session. We'll be exploring asset health, as the title suggests, in the context of the Common Network Asset Indices methodology, which is used by the electricity distribution network operators here in Great Britain. We'll be looking at each of the elements in the methodology and demonstrating how these elements are all connected. We'll be demonstrating some of the main principles behind the methodology, such as probability of failure, consequences of failure and risk, and we'll also be looking at how all these come together into a simple reporting matrix to support decision making and communication of results. The session itself is scheduled for an hour. We would expect the presentation section to be around about 40 to 45 minutes, with opportunity at the end of the session for questions and answers. So we look forward to receiving any questions you may have at the end of this session. So trusting that all sounds okay, I'll hand you across to Joanne. Thanks very much.
Okay, so good afternoon, evening and potentially morning for all of you. So not quite sure what time zones everybody is in, but it's nice to have you on the call. So I'm going to really lead the presentation today, the webinar session. So we're going to start by talking about what asset health is. So this is a nice clear definition. So asset health is a continuous numerical representation of asset condition. And you'll hear asset health, health score, health indices, health index. They all broadly mean the same thing. It's just a numerical measure of asset condition. It's a logical and consistent means of combining relatively complex information. And the reason we do this is so that you can, as soon as you're representing an asset in a single number, it's easy to look, it's easy to graph that number, it's easy to look at your worst and your best asset health. It's easy to look across and see whether they're meeting the right measures that you expect them to. It's an indicator of likely remaining life. So if you set up a methodology, you can determine what health score you might determine might be considered end of life for your particular own requirements. So we do see a variation there, and that will often depend on your appetite for risk and how proactive you want to be in terms of making sure you're minimising disruptive failures, but also maximising the lifespan of individual assets. It's not a substitute for engineering and judgment. So engineering and judgment, that all goes into the methodology in the form of calibration values and the data that you choose to put into the methodology. So you would still, even though you may be using a standard methodology as common methodology is quite a standard one in Great Britain, for example, and that's a useful methodology because it's It's widely publicised. You can get a free copy of that on the internet, and it's being used in various locations around the world, which we'll see in a minute. But the important thing is that regardless of whichever methodology you use, if it doesn't make sense to an engineer, then it's not fit for purpose for your organisation. So if the results, if you know an asset is poor condition and the health is saying it's not, you know you've got an issue with the health. So it's not a substitute for judgment or expertise. It should reflect that judgment and expertise. Okay, so just looking at some of the components of asset health before we get into the methodology in depth. So what goes in there is essentially an age, and this is an important component. It's useful when you don't have a lot of data. So when you've got data or assets which you haven't got a lot of condition information on, it helps get us started. But the principle behind like common methodology or CBRM, which we use, they are age modified by condition. So we do start from age, but we modify that by condition. So we're sort of saying that you'll never condemn an asset, or you'll never have an asset with a very high health indices until you know that you've got some condition issues with it. So for example, a steel tower might last in a very good environment, that might last 80, 90 years or even more, with minimal replacements. But just because it's that old, it doesn't necessarily mean that you're going to do much with that particular asset, but you'll continue to monitor that through the lifespan of the asset. And age is also important, as we'll see shortly, for when we want to project the assets into the future. We also have a nominal asset life. So for industrial customers, this tends to be set slightly lower, a slightly risk averse, or it could be the book life or accounting life of an asset. But in networks, we've tended to see, especially for things like transformers and switchgear, about 50 to 60 years is generally considered to be a nominal asset life. And we'll modify that nominal asset life as we move through the process, and for the individual assets. And then we need information about the degradation processes. And these are quite specific to the individual asset types. But in general, we're looking at observed condition measures, so collection from data, from field inspections, and also measured information. So that might be DGA tests, or for transformers, or it might be ductor tests or PD readings, things like that. So those are your degradation processes. And then finally, we're looking at current conditions. So we're also looking at things like the workload of the asset. So is it working very hard? And also environmental conditions. So we're looking at, is that asset indoors in a nice air conditioned substation, for example, or is that outside exposed to the elements? And if so, is it in a corrosive environment? Is it in high altitude where icing might be a problem? So the different asset types and the different inputs obviously have an impact on the asset health, and they go in to make up a health index. So in our definitions, so CBRM, which is our process, and also CNAIM, the common methodology process, we define asset health on a scale of, it's actually 0.5 all the way to 10 in the current year. And then for the future years, we do allow that to extend up to 15 years, but not indefinitely. But we're just trying to say that these assets have gone beyond reasonable expected life at a health index of 10 or greater. But in the current year, we use a maximum of 10. And so the lower the score, the better the health is. So, you know, an asset of 2 or 3 is in reasonably good condition, moving up to sort of poor condition where you might think about some interventions, and a health index of sort of 8, 9, 10, you're starting to think about end of life and what investments you might want to do with that asset to bring that asset back into reasonable condition so it's fit for purpose. So those are the scales that we use, and it's useful to put these definitions on, and they're quite broad definitions, which means that you can use them for an overhead line, a building, a road. You can use them for any type of asset, and you know that you're looking at comparable measures from asset class to asset class, and that's really important to have these sort of tradable, instantly known elements that you can look across, and that helps certainly with the reporting. And then once you've got an asset health, so per component, so per transformer, per conductor, per section of cable, you can represent it in a whole heap of ways. So this is just one representation. So assets that have a health of 0.5 to 1 go in the HI1 bucket. 1 to 2 goes in the HI2 bucket in this illustration. And so it's really easy to see from this population, this is just a sample of assets, that we've got a lot of assets down sort of HI1 to HI4. So those assets are about 60-70% of those of the assets in the population are in that range. So those who are in good condition don't need to do anything about those. Once you start getting to HI5, 6 and 7s, you're starting to think, are these refurbishment candidates, or should we leave them, and do they become replacement candidates? They're not replacement candidates necessarily yet, but maybe the HI8s, you're starting to think a higher increased probability of failure. We've got no HI9s, HI10s, so that's really good news. So that's a generally healthy but ageing population. And once you've established that and some rules for aging the assets, you can then apply. So in this case, we've aged the assets 8 years forward. And so we're now starting to see those HI9s, HI10s popping up in that population. And these are represented by that light blue colour, and a general shift. Going the wrong way for you guys. We've seen a general shift over to the right-hand side of the spectrum. For a lot of those assets. So you are going to be wanting to think proactively about these ones. So that's a really easy representation, and that works down at the asset engineer level, planner level, all the way up through to the boardroom level. So that's why Health Index is just so powerful as a visual aid. It's so useful to get meaning out of that, just any profile like that. So now we'll dig a bit deeper into the actual methodology. So as Chris said, this is based on the Common Network Asset Indices methodology, and we've got a link to that right at the end. We've got some links so you can have a look at that methodology if you've not seen it already. And it's like I say, it's as close as we've got to a standard. There is sort of nothing better, but if you do start looking at that or start implementing something like that, it will need adapting for your own environment, so for your own data points, for your own assets at your own voltages, and you'll need to calibrate the models. But it's really useful in the sense that it's got all these really standard algorithms, and that it's a really I'm going to say old, it's not old, it's a methodology that's been developed for a long period of time, and there's a lot of research and understanding gone into that, and it's as good a fit pretty much as anywhere, and any methodology that we've come across. So this just tells you a bit about the history, and we'll provide the slides at the end. But essentially, as I've just mentioned, we've been working with these condition-based methodologies since about 2000. Our background is in research and development, so a lot of the background was based on research work, either just by ourselves through our sort of data scientists and our asset engineers, but also with universities and with network operators. And their challenges, sort of 20 years ago, were lots of aging assets, old infrastructure. They could see potentially a bow wave of investments required based on age, and they weren't using condition at the time. And so gradually the process has evolved until we get to sort of present day, 2023, where we've got a very sophisticated but also relatively simple methodology. So there's some complex elements in there. There's a little bit of complex maths, but not very much. But it's generally a really good place to start. So Common Methodology version 2.1 is the one that's going to be in use by the network operators in Great Britain as of March this year. So that's when their next regulatory period starts. And that'll be in place for 5 years. And then we'll see some more developments on that methodology. So introduction of potentially more asset classes and things like that. But even in its current form, we've started to see customers and organisations in in Canada, the US, Australia, and Japan picking up that methodology and starting to use that for themselves, because it's, like I say, it's as good a standard as we're going to get. So this next slide shows us the relationship between the main modules in the health, and beneath each of these boxes there's another set of boxes, and we'll explore those in a moment, but this is essentially a big summary of the asset health methodology. So in the middle, most importantly, we have the current health score. You have to get this right, otherwise your future health score won't be right, and then the risk, when we look at that won't be right either, and the probability of failing. So the current health score is the thing that you really need to validate with your asset engineers. Does this make sense? And the asset health score is made up of the initial health, and this in turn is made up of age, expected life, operating environment, and workload. A health score modifier, which is the observed and measured conditions, and also a reliability modifier. And we'll take a quick look at each of these in turn. And then the future asset health, once you've got your current asset health and you know how old the asset is, we can create an aging constant, which determines that relationship with aging for individual assets. So assets age at their own individual rates based on things like workload, but also their current level of degradation and how fast it's taken to get to that point from a new asset. And so we can project that into the future. So our initial health score, so the red box down here just shows this is actually a calibration value, and we use calibration values to set values against a particular population. So a calibration value might be things like, in this case, it's a normal expected life. So for the individual asset types, so for a particular transformer type of a certain voltage or nameplate, you would expect it to last potentially 50 or even 60 years, and you would agree and set that nominal asset life, and then that calibration value goes to work across the entire population or fleet of those particular assets. And so you need to do that for each asset that you're modeling, asset type that you're modeling. But then the other inputs are by asset, individual assets, so they're calculations by individual assets. And so for our initial health score, we take the age per asset, we calculate an initial B1, initial aging rate, we calculate modified expected life and duty factor and location factor based on input data. And we'll look at the location factor now. So in the UK and other places, inputs are distance from coast per asset, altitude and corrosion. So these are inputs per asset. And in the UK, where there's a lot of coastline, distance from coast is quite important. If you're in a state that's in the middle of the country, distance from coast might be entirely irrelevant. And we've seen that as we've implemented systems in places like New Zealand, where, especially for things like towers and overhead lines, wind direction and jet streams and things like that has much more of an impact than distance from coast. Altitude is quite important, especially for lines, so for icing and things like that, and corrosion rating. So we use a score in the UK based on the Galvanisers Association. It's actually a measure of pollution and industry in a particular location, but obviously that's quite specific. But other areas will have areas of higher pollution and industry. And so if you're using this type of methodology, you'll want to swap out the things that don't make sense and swap in things that actually do make sense. But essentially what we're doing is we're bringing in these data inputs, we're modifying them with calibration values. So we're saying how important is distance to coast, for example. So for an asset which is like a transformer or switchgear, it's made of metal, the corrosion is going to be more significant because of the salt pollution in the air, for example. But for things like a wood pole, then doesn't really matter if that's close to the coast or not, usually. And so you would do the same for the different asset class, and you would calibrate the model in accordance with the asset class that you're looking at. And so you bring these things together and create an initial location factor, and the methodology, if you look at that, it defines exactly how you do that. And then we bring in whether the asset is indoor or outdoor, essentially. So as I mentioned, if you've got an asset in a nice air-conditioned sub and it's not subject to those environments, then you will reduce the effect of the asset inputs. But if the asset is outside and it feels the full force of those environmental conditions, then you would obviously take the full factors from the calibration for each of those assets. We also do the same for duty, but I haven't actually represented duty. And the reason I haven't done duty is because it's slightly different depending on the asset class. But essentially you end up with an input and then a factor is your duty factor. So for a transformer, we'd look at the loading. For a tap changer, we'd look at tap counts. Switchgear, we'd look at operations, etc. So those are the kinds of things we're trying to establish. So essentially workload. And some assets, so for a pole, for example, we just set that to be a neutral position because it doesn't really have an exact workload. So we just set it a factor of 1. So we do that for steel towers and poles and a few other asset classes where it doesn't have any sort of mechanical or electrical kind of parts. So I've tried to represent some of the formulas. And I'm not going to go through them in detail because otherwise it would take way longer than sort of our allotted 45 minutes for this webinar. But like I say, we'll pass the presentation pack, and I've represented the formulas as much as I can like this. So for the initial health score, we've got the as new health score, and then we're using an exponential function, and we have the initial aging rate and the normal expected life. And then the initial aging rate formula is represented down below. But I'll just explain the health score and the as new HI. So the as new HI is relatively straightforward. Instead of starting at 0, we start at 0.5. And the reason for that is because we're using that as a multiplier. And so when you multiply things by 0, it doesn't really work. So we start with 0.5. And then the actual health score, which I guess could be named better there, it's actually the health score, the maximum health score that we allow the asset to achieve based on its age, duty and location alone. And the reason we only allow this maximum of 5.5 at this point is because, as I mentioned before, we don't want to set a very high health index for assets that we don't have any condition information about. So if all you've got is age and maybe a bit of condition, maybe a bit of location information, then if it's old, it will get a 5.5, and you will need to look at those assets and say, well, some of these might be prioritised for inspection. And then if you inspect them and they come out good, so there's nothing wrong with them, then they sort of get capped at 5.5. But if you inspect them and there's some condition issues, then the health index would rise. And we use the initial health score as a multiplier. So we start multiplying that up, so you get a higher health score for those assets that are in worse condition. So again, formula for the initial health score, and there's a bit of an example there in terms of how we use that with that B1 aging initial aging rate that we just calculated a second ago. So once we've got our initial health index, we now want to look at our modifiers. So our modifiers are our specific condition information that tells something about that asset. And so the different modifiers will be different for the individual asset classes because you have obviously different inspection questions, different relevant tests and things. But for every modifier, we have a cap, a factor and a collar. And the factors are essentially multipliers. So ultimately, we combine all the multipliers and multiply that combined multiplier with the initial health score to get our final health score. So the factors therefore hover around 1. So a factor of 1 is a neutral position. A factor of greater than 1 will result in a worse health score than the initial health score, and a factor less than 1 will result in a better health score than the initial health score. The colours are there because no matter how old it is, sometimes the asset it has one or several poor conditions, but the asset is relatively new. So your initial health score would be very small, potentially very small, so like a value of 1. And if you multiply that by a factor, even if you multiply it by a 1.8 or 2, you're still not going to get a very high health score. So you're still not going to see that in a population. So the colours are there to say, and we set the colours as calibration values, and they're there to say, actually, we've identified a really poor condition element on this asset. We're going to automatically set that asset to a minimum value health score, and usually that's a 5.5 or an 8 value health score. So that's what the colours are there for. The caps perform sort of similar role, but they actually cap the health index, and they say, no matter what else you collect about it, we're going to cap this asset at the particular value. We don't use the caps very much, but to give you an example of where we do, if you think about like a wood pole, if the observed condition is quite poor, you might look at it and think, oh, it's not straight. The external condition looks a bit horrible. It doesn't look very good. So you might score that quite badly. But then if you then go and do a residual strength test and you see like the cross section of that asset and you actually realise that it's got good strength, then that would potentially override the poor observed conditions. So you might set a cap and say, actually, it doesn't look great, but we've tested it, so we know it's intact and it's fit for purpose. And so that's when we'd use a cap. But there's not very many instances where you get that really clear-cut reading of the fact that this asset is in good condition. For transformers, we've also got oil condition, DGA, FFA. So we are also taking in actual raw values, so what temperature corrected values for moisture, and then acidity breakdown strength for the oil tests. For DGA, we're taking the component gases, and for FFA, it's a measure of obviously paper condition for formaldehyde. So that information we're bringing through. For the DGA, we also look at the historic reading. So we're looking at historic trends as well and trajectories, because you might get one poor reading and then a good reading. So, or vice versa, it might be accelerating faster than you anticipate. So we put that into the methodology so that we're looking at the rate of change as well for the DGA. For observed condition, I think I've sort of explained this already. So every model will have a number of observed conditions. Common methodology specifies them for the 25 asset classes that are contained within it. But for other organisations, you'll need to adapt the observed conditions. But each condition has a factor, a cap and a collar, essentially. And we do the same as well for the measured condition modifiers. The reliability is something that we add on afterwards, and what we're trying to capture here is any asset conditions which we haven't already captured in anything we've done to date, so in the workload or the location or the observed and measured conditions. And quite often we see something like, if you've had a particular model of assets or a particular bad batch of assets between particular serial numbers, or that you've got certain assets which are just starting to fail, but they're not really captured anywhere else. Reliability is the place that you can add those in. It's almost freely available, but it's the important sort of catch-all if there's anything else relating to condition. And so the current health score then is the initial health score multiplied by the health score modifier and the reliability modifier. And they are subject to those caps and collars that I mentioned before. So the maximum of the collars, the minimum of the caps, but the collars actually do take precedent over the caps, which is confusing when you put it in, but it works. In terms of combining factors, I'm not really going to explain this in much detail. This is a common methodology way, it's a CBRM way of doing it as well. But what we're saying here is that you're going to take the worst factor, and if you've got any factors above 1, you're going to take the worst one, and then you're going to increment that a bit for every other factor that is greater than 1, and then up to a certain number of combined factors. And then if you've got no factors greater than 1, we're going to take the minimum, and we're going to take a little bit less if you've got more than 1 that's less than 1 as well. So that's how we combine factors, and you can obviously digest that when we provide the slides to you. So moving on to the future health score. The future health score is based on the future ageing rate, and we need the future year as a calibration value, or set future year, and the new health index, which we've talked about, which is the 0.5, that's your new position. And we also use an ageing reduction factor, and the ageing reduction factor almost acts as, it's a bit like expected life for people, in the sense that if you're in great health, so at birth your projected life might be, say, 81 years, approximately, in the Western world. But if you are, say, 75 and you're in great condition and you don't have any health issues, then actually your expected life might be sort of increased to sort of 85 years, for example. You might have, really good, you might be really lucky and last that long. So the ageing reduction factor is just to account for that you're expected to last a bit longer if you are obviously in good condition, and it's the same with sort of assets. So we take in the current health index, the age, and the initial ageing rate, and we use that to create the future health score. And I've got a formula for that as well. So B2, current ageing rate. Again, we're just using this quite simple function, and we've put the different parameters of the function in there, which we've already seen. And then the future health score uses that B2 value, so that current ageing rate, and then it ages that asset into the future, using the sort of exponential function. So that's health. Now we'll move on to have a look at probability of failure, and quick look at failure modes, but we won't spend as much time on that. We do have a webinar, I think it's, Chris, is it March, I'm going to say, all about probability of failure and failure modes. I see I've put him on the spot now.
I'll say yes, that's correct, but I will confirm we'll share the dates out for the next webinars, no problem.
Okay. So probability of failure, so this is your real shortcut value session on probability of failure. So as the health score increases, that's what we can see on the sort of x-axis of this, on this sort of diagram. And the probability of failure increases over time. And we've got this that way around for you guys. We've got this curve, so the probability of failure curve. So we don't use bathtub curve. We actually flatten that out to a value of approximately 4. We have a steady rate, a probability of failure rate, and then we use this cubic function to represent the assets aging into the future. So we've established this sort of relationship, and what we find is that the assets, it's set such as the assets at a health index of 10 have 10 times the likelihood of failure of an asset that's on the flat part of the curve. So that's how it's set up. And the way we use it is that if we get all of our assets and we know what our failure rates are, so we get all our assets and we can put them on little dots. If imagine putting on little dots all the way across your probability of failure curve, and then you've got your known probability of failure, so this is derived from your failure rate, and so if you put that in as well, and then you can actually calibrate and move those assets to the point on the scale where it meets that failure rate, and so that part of things establishes this nice relationship between health and probability of failure. So given any asset health, we can work out the probability of failure for that asset. And so that means that when we age the assets into the future using our aging algorithm, we can also project probability of failure into the future using that same relationship that we've established. And that's great because you can sum up your probabilities of failure, and that gives you your failure rate for that population. This is how it looks in the just in a diagram, just all the components feeding into that. K and C are constants, and so C is the constant that sets the steepness of the steepness of the curve, and K is a constant which sets the relationship between your probability of failure and your asset health. And like I say, more on that in 2 webinars time, and that will all be explained. And we have, like I said, this cubic function which we use to set the probability of failure. In terms of failure modes, so there's obviously lots of complex failure analysis and FMEA techniques and things that we can use. We use generally 3 failure modes that we establish as we establish the failure rates. We look at the proportions of the different types of failures, and we use these to set consequence values, which are monetized consequence values, as part of the next step, the step towards risk. Incipient failures are things like failure to trip and other annoyances that you have to go out and sort out, but they still take a little bit of effort to do. You don't necessarily lose supply, but they're still classified as a failure, and because they have a cost associated with that, either manpower or financial cost that you have to go out and do something, or like I say, you might have lost customers if it's an asset with no redundancy, for example. Then we've got degraded failures, so these are slightly more failures. So these might be failures of steel members and things on steel towers. So the asset's you've not lost the asset, but you know you're going to have to do something with that asset to make that asset fit for use and serviceable again. And then the catastrophic failures are the total loss of the asset, unplanned outages, replacement of that asset. And it's useful to think about these different failure modes as we set the consequence values, because generally the consequence values are set by these different categories. So that neatly brings us on to consequences of failure and risk. Fortunately, this part of the methodology is much quicker. So risk is very simply probability times consequence in this world. And consequences of failure in turn are a criticality factor, which is set per asset, individually per asset, and an average consequence. So the average consequences are what would we expect for a particular asset type in our population, what would we expect the consequences to be. And like I said, those consequences are all monetized. And so we also do that. We also set consequence values by these 4 categories. So network performance is also called security of supply, or it might be things like loss of production. It's the purpose for that asset being there. So if it was in an industrial plant or related to something that has throughput, that might be loss of production. So that might be a baggage carousel, for example, in an airport, and what's going on, if that fails to function. So the disruption and things that would cause, and passenger disruption, things like that. On the network, we're starting to talk about things like safety, or it might be the compromise in security of supply. So load not supplied, things like that. For safety, we look at aspects like it's really not the cost of life or injury, it's more the cost to prevent the life sort of injuries and things. And for different assets, we look at different inputs. So we generally have a location factor, so how close to people is that asset located, So if it's a densely populated area that the asset sits in, then there is more likely to be somebody in the vicinity if you have particularly a catastrophic failure of that asset. But if that asset is in a rural location, there's less likely to be people around in the event of that asset failure. So you can start to say, actually, this is more safety critical than that asset, and put some scales on that. Then we've got financial, which is quite straightforward, because that's just the monetized consequence of having to either do the repair or replace the asset or get that asset back into service. And then we have environmental consequences. So environmental would be things like disturbance, waste, loss of, say, SF6 into the environment, loss of oil to the environment, which are more significant if, say, obviously you've got oil in the asset, and then that asset is, if that asset doesn't have a containment system, for example, or that asset is then located close to a watercourse, there's obviously a more significant environmental impact if you lose one asset over another. And so the consequences, that's what we're trying to look at and set. And so these are some examples of the consequence categories again, and then the criticality factors and the things that we'd look at setting per asset that defines which asset is more or less important than another. And so the consequences of failure formula is looking at that reference cost, and then it's modified by the criticality factors in each of the consequence categories. And that's represented on this particular diagram. So your risk is then, in each category, is your probability of failure multiplied by your consequences of failure per category, and then you can sum those up to get a value of total risk for an individual asset. And because you've got the total risk, which is in a monetized form, you can do that per asset, you can do that per fleet, you can do that per substation, per circuit, per network. You can roll that up and you can cut and split and decide, even by a manufacturer. So you can do lots of analysis on the risk, and also because you're doing the same process in different asset classes, you can then look at the different risk in different asset classes. And what you can also do is you can do the risk now, the risk in the future, quite simply because you've aged your assets, and you can do the multiplication again. But then what you can also then go on to do, again, subject of another webinar, is you can start saying, well, if you replace that asset, you're going to get an asset of, say, 0.5 again. And so you can work out the residual risk of replacing individual assets, and therefore you can work out what we call the delta risk, so the difference between the current risk or the future risk and that residual risk, and that will give you the amount of risk you will reduce off the network by replacing each and every asset. And so you can work out which are your highest contributors to risk, and you can use that as a prioritization for replacements going forward. A couple of final things. Communicating results. Talked a bit about this as we've gone along. A couple of screenshots just to show you. So this first one is very simply asset by asset, the lowest level of sort of detail per asset, and then you can get things like your current health scores and probabilities of failure, and you can obviously endlessly play with those in Power BI or Excel or any tool of your choice. Representation of the asset health. In this case, we've got a matrix. So in this matrix, assets from 0.5 to 3 are represented in what we call a HI band 1, and then 0.3 to 5.5 are in 2, and then 5.5 to 6.5 is in 3. This is testing my knowledge. 5, and then up to 8 in HI5, and the remainder in HI4, and the remainder in HI5. And the reason we split these bands up unequally is because we can create this really nice little small matrix that we can communicate across any asset class for now and the future with interventions, and we can see what's going on. It's a really nice visual picture, but essentially we're looking at replacement of the HI5s for sure, the HI4s, refurbishment, possible replacement, and then the HI3s, maybe in the future we need to do something. HI2s, HI1s don't need to worry about those. So they immediately tell us a nice story about what's going on with each asset population. And obviously, like I say, because you've got this nice common standard between all your models, you can do this in terms of substations or networks or regions or whatever granularity you want. And then the other parts of the matrix, the C1 to C4, just represent the criticality of the asset or the consequences. So C1 is less than average consequence, C2 is an average, and then C3 and 4 are greater than average consequences. So the worst scenarios are your got none here, but HI5, C4 assets. So those are the ones that are your priorities for investment into the future. And then you can start working out, do you want to do your HI5s and get your worst conditions, or would you prefer to do some of your HI4, C3s, which we've got one of those. So you can start trading criticality and health depending on what you're prioritizing. Just one final screenshot. This is just a shot from our Invest software, and this just shows you, again, just another method of communicating results. So we've got assets represented in clusters with different colours, so traffic light system, so good, bad, not so great, in the red, amber, green around the middle. And so again, it's just a nice visual picture in terms of representing an asset population.
Excuse me, Joanne,
Yes.
We're still on communicating results slide. We didn't see
that one. You're on that one. Yes.
Yeah, we're still on the PowerPoint, not the slide 39.
That's weird. I'm moving forward. You see that?
Guys,
maybe
it's moving for us.
Yeah,
okay. Sorry about that.
You're up to slide 41, I believe.
Yeah, that's good.
We're looking at 41.
Brilliant. That's what we want. Okay. And then just a few bits and pieces. So just to wrap up and leave us 10 minutes for questions. So if you need any more information, so that's really your presentation sort of done. If you need any more information, obviously there's me and Chris who you can contact. There's a whole load of links and things. We've done lots of, like I say, lots of research around methodologies and things. You've got common methodology links in there, which we'll share with you. There's lots of sort of papers and things like that. On the second page of this, these don't have links, but we can provide. They're usually proceedings from conferences and things. So some of these are with some of our customers just to show how they've implemented this kind of methodology. Others are sort of other studies and things like that. And it's over to you guys in terms of any questions. I appreciate that that really is a whistle-stop tour of asset health and risk. And so I hope I've not sort of I've managed to keep everybody on board.
A lot of information to take in. Thanks very much, Joanne. Just actually answering your initial question, Joanne, around the dates for the future webinars. I can confirm that to give people thinking time for questions. We have coming up using risk tolerance thresholds to set replacement criteria. That's on Wednesday, the 22nd of February. We also have defining failure rates and probability of failure on the 29th of March. After that, we also have another one in April, on April the 26th, asset model data requirements. We'll follow up obviously with these dates and the slide deck after the session, but just to answer your initial question, Joanne. Caught me on the hop.
So please feel free to unmute yourselves or ask any questions in the chat. So quiet. Have many of you come across sort of this type of methodology, or is anybody sort of implementing this on your sort of asset bases.
I've not seen this before.
Okay.
No problem. Well, it seems to be quiet on the questions front, but obviously there is a lot to take in there. As Joanne mentioned, you have our contact details, and any questions you do have beyond this session, please do reach out. Jeffrey, yeah,
question.
please feel free.
Yeah, I'm just wondering, I would appreciate if you can forward the PDF file so that I can share it with others. And it's quite a bit of information to
Yes.
to grasp and get it and understand. So yeah, if you can forward the PDF file, then I can go through and ask the questions later.
No problem at all. That's absolutely fine. Yes, we certainly will be sharing out the slide deck.
Thank you.
No problem.
I think we've stunned everybody into silence.
Stunned silence.
Stunned silence. Yeah.
No problem.
I appreciate
well,
it is a whistle-stop tour, and I was thinking when I was putting the slides together, maybe we should have just done asset health so that we could have spent just a little bit more time going through that in a little bit slower. So maybe after we've done this webinar set, maybe that's what we'll do, and break it up into a few more sort of more digestible chunks. But hopefully that's given you a feel for everything.
Yeah, absolutely. Just leaves me to say thank you very much, Joanne, for the presentation. Really detailed, thoroughly enjoyed it, and thank you all for joining us. It's much appreciated. If you do have any questions, again, please do reach out to us. You know where we are. Okay.
Thanks
Thanks
everybody.
very much, all. Take care.
Thanks for joining. Bye now.